Welcome back to Rusty Road Trips, and today we're going to be doing something a little bit different. We're going to be kind of going over this automatic transmission Lego car that I built, as I got bored the other day in my apartment and I'm here at school, so I do not have the ability to go work in my shop at home on my trucks and other vehicles. So I just busted out the old Legos here and ended up taking and creating this 3-speed automatic transmission using a series of differentials and gear ratios. And so gonna kind of run through how I built that and then show you how it works, and hope you enjoy. So to explain how my Lego transmission worked, I decided to put together a little bit of a presentation after crunching some numbers, doing a little bit of MATLAB, and otherwise geeking out. So this transmission was based off a couple ideas I derived from the following formulas. And that comes down to the center two versions of this formula, which is with gear ratio and speed. Now I noticed that these two have an inverse relationship, and we also can hold a number of things constant. So in our case, given our setup with the electric motor, we can hold RPM, tire diameter, and obviously 336 constant. So that results in the inverse relationship. Now, an inverse relationship, if you don't know, is this graph on the right, where we see y is equal to 1 over x. Now, this graph has a negative portion, which we see in quadrant 3, and a positive portion, which we see in quadrant 1. We are only worried about the positive portion in quadrant 1. So moving forward, we need to find our constants. So in this case, we're using this type of electric motor, which is a Lego motor, and in my case, all I'm doing is running it at 1 speed. So after a little bit of Googling, I found out that this motor runs at a constant speed of 450 RPM. So now we have that constant, we need to figure out what our tire diameter is. Now the tire diameter that we are using is 56 millimeters, and in this visual you can see right down here in the lower left, that is the tire that we're using. And we need to convert this to inches because that is what our formula requires, and a little bit of conversion gives us 2.2 inches. So now we have the two unknowns, which is RPM and tire diameter. So now we also need to figure out what our gear ratios are, because we will have a variety of gear ratios. Even though in our function I'm going to leave gear ratio as just a typical variable, we will have to find on that line that we graph where the gear ratios that we are working with are to determine what speeds we'll be running at. So from this visual up here, you can see that we're using this type of differential with this type of gear, and we can follow that to see it's 1 to 1.4. We can also see that we are working with this larger gear against this smaller gear, which gives us 1 to 5. And then we can also see that we're just using a 1-to-1 gear ratio for our output from the transmission, and we can also see that we're using this medium-sized gear to the small gear as well for a 1 to 3. So moving forward, we can crunch a little bit of math and figure out that our first gear is a 4.2 gear, our second gear is a 1.75, and our third gear is 0.84, which will be our overdrive. All of this is calculated through this equation we see at the top, where final drive is equal to input gearing times transmission gear times differential gearing. And as I said, our differential gearing is 1-to-1. Our transmission gear, we have 3 options, which I stated before, and then our input gearing is that differential to that yellow gear. So now that we have the points on the graph that we need to find, we can go ahead and create our equation. So given that we know RPM, tire diameter, and obviously 336, we can determine that in our equation that's just going to be one constant held at 2.95. And then we're treating speed as our y variable and gear ratio as our x variable in this case. So our final equation is speed is equal to 2.95 divided by gear ratio. So doing a little bit of MATLAB work so I can plot this, we get this final plot. And you can see that in first gear, we are going to be going about 0.7 miles per hour. In second gear, we can go 1.68 miles per hour. And then in third gear, which is our overdrive gear, we can go a walking pace of 3.5 miles per hour. So why does this actually work? We can see that gear ratios affect speed, but why does having a series of differentials actually work to change the gearing? Well, differentials kind of follow the path of least resistance. So using that principle, we can look at these governing equations on the left, where the RPM of one side of the differential plus the RPM of the other side of the differential is equal to 2 times the output or input RPM, depending on how you're using the differential. Also, the torque times the RPM of one side of the differential plus the torque in the RPM of the other side of the differential is equal to the output of the power and or the input of the power. Again, depends on how you're using it. Now, when I mean depends on how you're using it, if we look here at our input torque and input RPM, we are using it where instead of saying power out, that's our power in. But if we look on the other side where we're taking and driving the wheels, that's going to be power out because we're driving 2 different RPMs and 2 different torques from each side, which is being put into that differential. Now, our gear ratios will change from each side of this initial differential. So as you follow it down, we're going to get a split in torque, but then that's going to be multiplied out on different sides, given this final equation over here where we have gear ratio times input torque equals output torque. So this gear ratio in this case is 1 to 1. So whatever split here is just what ends up here. And on this side, we're multiplying our torque out because we're going from a smaller diameter gear to a larger diameter gear. So on this side, this would be our first gear. On this other side, this would be our third gear. And then because this function doesn't have any discontinuities in it, we will have a second gear where these will be running at equilibrium. So if that didn't quite make sense, here are the graphs that I think help visualize it a little bit better. So this graph on the left is just the graph of the function of our input torque times our gear ratios. That gives our output torque. So the larger our gear ratio is, the more output torque we get. And then on this side, we have the relationship between required torque at a constant speed. So for example, in our case, manipulating the differential governing equations as well as the vehicle speed versus gear ratio equations, which we looked at the beginning of this presentation, we get this equation down here below where it's input torque times RPM times tire diameter, and all of that's going to be divided by 336 multiplied by the speed, which is equal to our output torque. So in this case, when our speed changes from a lower speed to a higher speed, we need less of an output torque at the wheels. Given our input torque is constant, given our electric motor runs at 1 speed, 1 torque, etc., etc. So that's, and remember how I said that the differentials follow the path of least resistance? Well, with our lower gearing and at a lower speed, we're going to want the higher amount of torque given this function. So we're going to want first gear. But as we increase our speed, we need less torque, but we need higher RPM. So in this case, we're going to shift to second, somewhere in here. And so then in our final overdrive, which is at 3.5, we're going to be in our highest gear and our lowest amount of torque. And we can see that in the video, whereas it's on the flat, we're in second gear, and it needs less torque to maintain that constant speed. But as soon as we go up the hill, it slows down and shifts into first gear because the amount of torque required at that lower speed is much larger, so we go to first gear. And as well as going down the hill, we are now going to want it to go at an equilibrium speed of much faster equilibrium speed. So we're going to need less torque at the wheels to get the vehicle moving and keep the vehicle moving, so we'll be in our overdrive and our higher gear. And that is just kind of how this Lego transmission works. Now, this is confusing. Let me know. I can try to put something together a little bit better. But this was kind of me trying to explain everything that I was kind of thinking out and put all the chicken scratch I had from my notebooks and my whiteboard and everything into a presentation.
So the way that this automatic transmission works is quite simple. We have it driven right here by this continuous speed electric motor, which goes into this first differential here, which, if you know a differential, it kind of follows the path of least resistance like water. So we have output to the larger gear and then output to the smaller gear. Following the front side here, we just have a series of 1-to-1 ratios until we hit that larger gear. The reason for that is we needed 4 gears on this side, as we have 2 gears on this side, so that we can have the same, we can be turning in the same direction, but also having 2 different gear ratios. Now, on the opposing side here, we have a large gear driving a smaller gear for our overdrive, and obviously with a small gear on a larger gear on this side, this is going to be a lower gear. So the way I have this set up is that this is first gear, equilibrium between the two is second gear, and then our third gear in overdrive is this side. So those drive out coming from this original shaft right here on each side, the black ones, and then they come down the side and then they drive the second differential here. So then in this differential, again, it's going to follow the path of least resistance and then turn the entire differential assembly, as the way Lego has it set up, driving the rest of our car. So now that we kind of have the basic explanation of how this works, I'm going to take and run it right now, and we're going to take and see how this works. So currently we are in second gear since there's no resistance on the system. So equilibrium currently is going to be just all gears rotating at whatever speed that they can. Now as we put a little bit of resistance on here, you can see that we're now slowing that larger gear and spinning more on this lower side. And now watch that larger gear here. When I release the resistance, it spins back up again. So now we're in second. Now resistance, we're down into first. And the more resistance I put on it, the more it biases the more torque heavy side. So the side that's producing the most torque. So let me just put resistance on the system again here. See how that far gear in the background is slowing down, and we're now biasing towards the front more, and now I release it and the whole system spins up again. Now I got to reposition this real quick, and I'll take and show you the function of overdrive. So since our motor only operates at one speed, and using this differential assembly as our transmission, we're always going to follow the path of least resistance. So putting something into overdrive is a little bit difficult unless we're going down a hill, and to allow the car to speed up and the motor to remain speeding at a constant speed, overdrive is necessary. So since we do not have this case currently, I'm just going to lock out our first gear so that we're stuck in overdrive. So we're going to start it up here. And as you can see, as I start locking this gear out, we just run purely in overdrive and see how fast everything's spinning, and then I'm going to release it again, and we slow back down. And you can even watch the wheels up here. So we're now just in second gear equilibrium. I lock out first gear, see how fast that's spinning, and then release it again. And now I'm going to lock it overdrive and see how much slower it's spinning. So this is first gear, second gear, overdrive. So I have the car put back together, propped up on a little test stand here. We're going to run through it one more time and show you the 3 speeds. So we're going to currently lock her into first gear. So looking at our wheel here, that is first gear. And then we're going to release it, second gear. So that's spinning much faster. And lock it into overdrive. And then back down, second gear. Locking in first gear. And I'm just doing that to lock in first gear. I lock out the overdrive gear, so the only possible ratio it has to spin on is the equilibrium of first gear. Releasing that is the equilibrium between overdrive and first gear, which gives a second gear, and then locking out First gear gives me only having overdrive, so then everything spins at overdrive. And then I'll show you on a series of flat terrain, inclined, and downhill how the car will shift between the 3 gears on its own to allow that electric motor to spin at its constant speed. So I have the car here set up on its test track, which goes from this flat terrain here, which is the textbooks, to the table sectioning, which is an incline, up underneath the coffee table onto the board games, which is going to be our flat terrain again. So let's get her moving. So currently she takes off in first, goes in the second. Now as we climb up this hill, you can see that we are locked into a first gear, and as we come up to this plane up here, we're back down to second. Now it's going to go very fast down the hill because it's a very high overdrive, but remember that motor is spinning at a constant speed, so that's where our transmission is taking over and going into overdrive. So let's take and send it back down the hill, which moves extremely fast, and then back down on the flat. Now one more time, we're going to take and bring it up the hill here. We're going to stop it. I have not even touched the car, and we're going to hill launch again. And she goes right back up because she can pick the gear that benefits the car the most. And then stop here again, and then one more time down in overdrive. Perfect. So even though this wasn't the most interesting automotive content you've seen out there on YouTube, indoor and actual car, this is just something that I threw together here in my apartment some Saturday afternoon, and figured I'd put it out there and share. But you can still tinker even if you don't have all the tools on hand, and learn about the systems that actually allow a car to run. And so to get out there, get working, and enjoy your day. Thanks.